Hi everyone. So today we're going to be actually talking about work with this chapter of work and energy. So far we've only been talking about energy, but today we're going to be talking about work. So in which scenario is positive work being done, zero work, negative work? What we should know is work is equal to the force times displacement times cosine of theta. Okay? So this is the key thing. And it's important to know that work, how I like to think about it, work is done when a force is applied and that force is bringing about results or bringing about a distance. So force is bringing some results in the form of distance. Maybe it seems kind of weird, but that's how I like to define it. Okay, so let's look at this one. We have force that's going up, and this is moving to the right. So what we can see is, even though this force is going up and there is a displacement, what we can see is the object isn't going up at all. So even though there's a force going up and it's moving to the right, there's going to be zero work happening because the force isn't helping with it moving to the right at all. And in this case, there'd be zero work. Another way we can know that there was zero work with this is because we know if we were to look at this equation, force times displacement times cosine theta, we can see the angle between the displacement and force is going to be a 90-degree angle. And we should know cosine of 90 is equal to 0. So this would just be 0. Now look at part B. We have force going to the right, and we also have displacement going to the right. So yes, the force is resulting in some distance, meaning there is positive work happening here. Okay? And we know when the force and displacement are going in the same direction, their angle is going to be equal to 0. And we should know cosine of 0 is equal to 1. So that's when the maximum amount of work is being done. This one we can see the force is going to the left while the displacement is going to the right. Okay, so we can see that actually, even though this force is trying to make it go to the left, it's going the other direction, which is going to be 180 degrees. So this is doing negative work. So it's going the negative direction of which way the force is trying to make it go. So it's negative work. And that should make sense because we should know cosine, again, of 180 is equal to negative 1. Okay? I hope that helps, but when we do some examples, it's going to make some more sense. Alright, let's look at this first one. A teacher applies a force to a wall and becomes... is there work for the following situation? A teacher applies a force to a wall and becomes exhausted. Okay, so if we have this wall here, teacher's pushing it like this, there's not going to be any work. No work, and the reason why there's no work, because the wall doesn't move. So no matter how much force you're applying to it, we don't do any work unless something is moving in that direction of the force. And if the wall isn't moving at all, so zero work. Okay? Next one. A book falls off the table and free falls to the ground. Is there work for the following situation? So what we have a book. The book is falling down like this. Is there work? There is actually going to be work. Force of gravity is going to be pulling it down, and it's also going to be moving down. So we can see gravity is doing work. So in this case, force of gravity doing work. Okay? Next one over here. A waiter carries a tray of food above his head with one arm and moves straight across the room at constant speed. Okay, so this one's going to be a little interesting. This waiter has food here, blah, 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 and whatever he's holding. And he's moving to the right. So we can see that the food is moving to the right. However, he's applying a force straight up. So actually, he's not doing any work with his arms. Okay, he's not lifting it up or going down, and it's going to the right. And this is going to be a 90-degree angle, so there's going to be zero work happening here. Okay, the force is not helping it move at all. A rocket accelerates straight up into the air. In this case, we have a rocket. It goes straight up in the air. There's going to be a force of the thrust as well as it moving up. So there is going to be work being done to it. The force of gravity in this case, which is going down, is going to be 180 degrees. So the force of gravity is actually going to be doing negative work to this, trying to prevent it from going up as high. Okay? All right, so let's look at some problems here. A hockey player exerts his 4.5 Newton on a 0.105 kilogram puck, which starts from rest and slides across the ice for a distance of 0.15 meters. Draw a free body diagram, how much work is done, so on and so forth. Okay, so let's look at this problem. A, free body diagram. We have a puck. There's going to be a force of gravity. We're going to have a force applied, force normal. There's no friction done by it because it says ice, so we're just assuming that there's no friction. So force of gravity, this is going to be 1.05 newtons. Force normal, 1.05 newtons. Force applied is going to be 4.5 newtons. Okay. I'm going to actually change the color of this, so I should have done this a while ago, but whatever. Okay, and we know that this is moving also to the right 0.15 meters. Okay, it's moving to the right 0.5. Okay, now let's look at part B. How much work does the player do on the puck? So we should know that the work done by the player is by the force applied. So work applied is equal to force applied times the displacement times cosine theta. So let's try to figure this out. The force applied is 4.5. That's how much the player does. Displacement, 0.15 meters times cosine. And we can see that it's moving to the right and he's pushing it to the right. So the angle is going to be 0, which makes cosine 0 just 1. So we can see that the work done by the player is 4.5 times 0.15 times 0.15. And we get 0.675 joules. This is how much work he does on the puck. That's the player. Part C, how much work is done by the force of gravity? So we can see force of gravity straight down. So we're going to do work of gravity is equal to force of gravity times displacement times cosine of theta. We can see force of gravity is 1.05. Displacement, again, 0.15. But now the tricky part is this theta. We should know force of gravity is going straight down. Displacement is going to the right. So the angle is 90 degrees. And what we should know, cosine of 90 is 0. So that makes this whole thing 0 joules. Work does 0 joules of work. Okay? All right, part C. Part D, how much work is done by the normal force? So we're going to look at that again. Work of normal force is equal to force normal times displacement times cosine of theta. Same thing, normal force is 1.05. Displacement is 0.15. Oh, sorry, this was 0.15, but it doesn't matter. 0.15. And cosine, again, it's moving to the right, but force normal is straight up, so this angle is 9 degrees, meaning this is 90, meaning this is 0, and this whole thing becomes 0 joules. Okay? Now, let's look at part E. What is the change in the puck's kinetic energy? Okay? So when we're looking at this, there's a few things we need to do. Part E. Let's see. Part E. What we should know is change in kinetic energy, first of all, is equal to 1/2 mv final squared minus 1/2 mv initial squared. Okay, so kinetic energy final minus kinetic energy initial. The good thing is it starts from rest, meaning this just becomes 0. So we have to figure out what this final velocity is. Next thing that we know that we can try to find out is we can find out what the acceleration of this is. So what we should know, maybe I'll do this in a different color because there's so much going on. I don't want to confuse people. So what we can say is let's look at sum of all forces in the x equals mass times acceleration x. We have one force in the x, 4.5, which is equal to the mass, which is 0.105 times acceleration. And we find that the acceleration is 4.5. divided by 0.105, 42.86 meters per second, 42.86 meters per second squared. So that's the acceleration. We know initial velocity is 0. We know displacement is equal to 0.15 meters. And now we can find the final velocity because we have 4 pieces, and 3 pieces that we know and the 1 that we are looking for. So we can say final velocity squared is equal to initial velocity squared plus 2a change in x Final velocity squared is equal to 0 plus 2a, 42.86, times displacement, 0.15. And then let's find what this is. 0.15 times 42.86 times 2 square root, and we get 3.58 or 3.59 meters per second. Now that we know that, let's plug it back into this equation here. I'm going to change my pointer real quick. But what we should know is, okay, change in kinetic energy equal to 1/2 mass, 0.105, 3.59 squared. And let's see what we get. 3.59 squared times 0.105 times 0.5. And we get around 0.676. And what we should notice, the change in kinetic energy here is also going to be the same as the change, as the work done. The total work done, 0.676 joules, is equal to the total work, 0.675 plus 0 plus 0. Okay, it's a little bit different because there's a little bit of rounding, but pretty much same thing. I know we did a lot of work to show that, but just a little proof there. Okay, we're going to do one more. Okay, a sailor uses, or maybe two more. A sailor uses a rope to pull a 40-kilogram boat a distance of 30 meters along a dock, making a 25-degree angle with the horizontal. How much work does the sailor do on the boat if he exerts a force of 255 newtons on the rope? Okay, so we see the sailor is doing 255 newtons. So first one, we should know the work applied by the sailor is the force applied times the displacement times cosine theta. One thing we should know is this boat is going directly to the right 30 meters. Okay, so this is going to be equal to force applied, which is 255, times displacement, 30, times cosine, and the angle, so this angle is going straight 25 degrees. So the angle between the force and the displacement is 25 degrees. Now let's see if we can figure this out. 255 times 30 times cosine of 25 gives us 6,933. All right, 6,933. There we go. 6,933 joules. Part B, what is total work done? Okay, so what we should know is there are a few forces acting on this. There's going to be force of gravity going straight down, force normal going up. Force of gravity is going to be 400. Force normal is going to be 400. But what we should know is that the work total, the work done by gravity is going to be 0 because it has a 90-degree angle with the displacement. And the force normal, the work done by the force normal is also going to be 0 because, again, it has a 90-degree angle with the way it's moving. So it's not affecting, it's not doing any work of both the normal force or gravity. So the work is only done by the sailor, which is 6,933 joules. Okay? And part C now says, what is the speed of the boat after it has traveled 30 meters if it starts with an initial velocity of 2 meters per second? So we can kind of use some Newton's laws and kinematics to figure this out. But right now, what we're going to do is we're going to use work. Work total, we should know, is equal to the change in kinetic energy. So we know the work total is 6,933, and it's going to be equal to 1/2 mass 40 velocity final squared, which we're looking for, minus 1/2 mass 40 velocity initial squared, what they say is 2 squared. So let's do a bit of math. 6,933 is equal to 20 VF squared minus, so it's 4, 2, minus 80. So let's do this. 6,933 plus 80 divided by 20 square root 18.73. 18.73 meters per second. Okay? Hope that made sense. Or let's finish with this last one. A boy exerts a force of 11 newtons at 29 degrees above the horizontal on a 6.4 kilogram sled. Find the work by the boy if the sled moves 2 meters, assuming the sled starts with an initial speed of 0.5 meters per second and slides horizontally without friction. Alright, first of all, sled, 11 newtons, 29 degrees, 6.4 kilograms. So there's a force of gravity, 64 newtons. Actually, we don't know what the normal force is. We know it's less than 64. But let's first find the work done by the boy. Okay, done by the boy. So work applied. Force applied by the boy times displacement times cosine of theta. Force applied by the boy, 11. Displacement, how far did this go? 2 meters. Times 2 times cosine. So again, this moves 2 meters to the right. So that means the angle between the displacement and the force is 29 degrees. So let's do this. 11 times 2 times cosine of 29. 19.24 joules. Okay. Part B. If the frictional force is 2 newtons, what is the work done by the frictional force? Oh, okay. So now we have force of friction over here. And we have 2 newtons. So part B now is work done by friction, which is going to be the force of friction times displacement times cosine of theta. Work done by friction is going to be equal to friction, which is 2, times displacement is going 2 to the right, times cosine of theta. So we know it's moving to the right, but force of friction is going to the left. So the angle between them is going to be 180 degrees. And this is going to be equal to -4 joules. Part C, what is the total work done? So we know work total, in this case, is going to be equal to the work applied plus the work of friction plus work of gravity plus work of normal force. So this is going to be equal to 19.24, work of friction minus 4. And we should know work of gravity is going to be a 90 degree with the angle. So work of gravity is going to be plus 0. Same thing with normal force. It's going to be a 90 degree angle, so that's also 0. So we should know this is going to be equal to 15.24 joules. Okay. So I hope that made sense. Thank you guys for watching, and we're going to continue doing a little bit of fewer harder problems next time. All right, guys. Thanks for watching.